Welcome back, everybody. So I wanted to make a quick mention about countable sets. They are, of course, very important throughout all of math. They are the smallest infinite cardinals are the countable sets, and they show up all over the place. And they're also like a lot of the combinatorics is much easier when you have a countable set, so it's important. They're important when you have them, right? So the definition that we're going to use is that a set A is countable if and only if there is a one-to-one function from A to B. So equivalent if A is dominated by omega. Okay? So notice this allows A may be infinite or finite. Finite or infinite. Right? So we know that if it's a proper, if it's any subset of omega, we showed already that if a subset of omega is either equinumerous to omega or is finite, right? Remember, we showed every non-finite subset of omega must be equinumerous to omega. So, and in the case it's finite, we get that A is equinumerous with omega, and in this case, we get that A is equinumerous by definition with a natural number that belongs to omega, right? So, both are called countable. So if you want to talk about the case equinumerous to omega, we usually say infinite countable. This is an infinite countable set to refer to equinumerous to omega. Okay, so another equivalent definition, as we saw in the previous video, is the same as saying that there is an onto function. So it's the same. There's an onto function from omega to the set A, right? That's by the previous video, those two are the same. Let me write this in a different way. So here, say equivalently, this is the same thing as saying that there's a sequence, and they think of this as a sequence, as an onto function that maps the number n to the element a sub n from omega to A, such that A is onto, so that A is an image. By this here, I'm saying A is the range of the function little a. Of the function that maps I to AI, right? So that's exactly the same thing as saying it's an onto function from omega to A, that I'm just enumerating the elements of the image of the function. But this definition makes the name countable more clear, right? Because you're exactly A here, this is the set A. Here, these are all the elements of the set A. So essentially, you're counting the elements. So a function like this gives you counting of the elements of A. There's a zero element, one element. So you find a counting of the elements, and that's why they are called countable. Okay. So if A was finite, you will have to repeat this sequence doesn't need to be one-to-one. So you may have to repeat the same element many times. That's allowed by that statement up there. And in the case it's empty, we also call it countable. But in that case, you won't have a sequence like this because you have to fall somewhere. That's why I say in the case when it's not empty. But empty set is also a countable set. Good. So that's the definition of countable. And this is an important theorem, which might be very obvious, but it requires a proof using the axiom of choice. So it's worth at least looking at it and figuring out where is that we need the axiom of choice to prove this theorem. It says that a countable union of countable sets is countable. Okay? So there is one thing that we know already, and is that omega times omega is equinumerous to omega. Yeah? So this is the plane, omega times omega. Why do we do it like this? And this is on the same proof we did with the rationals, saying that the rationals are equinumerous to omega. We kind of put the rationals in the plane, P over Q, so we had the pairs P comma Q, and then we went through all of them and we did a counting of all of them. Same thing here. Okay. So this is very similar to that, right? So omega times omega is countable in many columns of each one is omega. But why did I say we need the axiom of choice to show this? Well, this here is a proof. Let me do a proof. So let's start with a countable collection of countable sets, like what we have in the theorem. We want to show that the union of this collection is countable. All right. So what do we know? So first, let's assume that its collection is not empty. Otherwise, the union is empty. and is countable, and that none of the sets inside are empty, because otherwise you just remove them from the union and they don't add anything. So you might as well think there is no empty sets involved here. That means what I just said is an argument that we can assume is not empty. So it's not just a disregard. You have to think about why that argument I just made sense. Okay, so they are all countable and not empty. So for each a that belongs to A, there is an onto function f from omega to A, right? And now what we want to do is put these functions all together into a function from omega times omega to A. So we also have an onto function g from omega to the collection A. So that means g assigns each element in omega, each natural number, a set within the collection A. Okay? So essentially, maybe let me draw a little picture of this. Here is omega, and let's draw A. So A is a collection of sets. These are the ones that I'm calling Roman A, but they are different ones. And then this function g, it maps to each one of them. This one, this one, this one, this one, this one, and it goes to each set, right? And then we have, for each of these sets, we have a function f that goes from another copy of omega, and it maps them all onto inside this set. This is f. And then we have another one for this set, and we have another one for each set. We have another function. These are the f's that we have for each, right? And now we want to put them all together. Okay, so we define h from omega cross omega to union of A as follows. We define h of pair n comma m that belongs to, and we let it be what? Okay, so if we say, suppose your n is here, this is the first n, the first coordinate, and this is pointing to this set right up here through, this is we say this is g. So we're gonna look in g of n, and now in g of n we're gonna say, okay, now where is m going? And then suppose m is here, and then m is being mapped to whatever guy inside there, and this is a function f that corresponds to this particular set A, right? We have a different function f for each set, so you're gonna say f of which f? The one that corresponds to g of n applied at m. Makes sense? So this function here that depends on A, we call it f sub A, right? So we know that for each A in A, there is an onto function from omega to A, call it f sub A, and then that's the one we are using here. What A are we using? We're using the A that comes from this n up there, okay? So this function is onto, right? Because G is mapping you, is giving you all the possible subsets of A. So whenever you have this M, you're going into all the subset of A, of the collection, all the sets of the collection. And then for each set in the collection, we have an onto function from omega giving you all the things inside, and this one, all the things inside. So this function is onto. You should double check that. Don't believe me on what I said. And okay, why did I say this was tricky at all or anything? It's not tricky, but why did I say it needs the action of choice? Where is the action of choice being used? The action of choice being used right here. Action of choice. Why is that? Well, we know that for every A there is an onto function like this, but actually there are many. And we're choosing one for each A, right? So we have to choose one for each element of the collection. For each of these circles up here that are infinitely many, you have to choose one onto function, f of A, into it, out of how many. How are we choosing that? There's no best way to choose that, or it's not constructible way to choose that. We need to use the action of choice. Let me see how we do that. Let me copy this part. That's what we had in the previous slide. And now, why is that we're going to got this f of a? So essentially, we can use any of the various of the equivalent definitions of the axiom of choice to use this one. Let me use the one with relations. So we can define, so let R be the set of pairs A, F, such that A belongs to the collection, and F is a function from omega to A and it's onto. Okay, so by our previous observation, we get that for every A in the collection, there is such a function. So that means that all the A's inside the collection, the domain of this relation is actually everything. So all the A's show up. The question is how to choose one such function, right? And now we use the axiom of choice to get a function f, subset of the relation, with the domain of f equals the domain of the relation, which is A. And this function satisfies, because it's a domain is everything and f is a subset of the domain, we have that for every set in the collection, this function applied at A is going to output. What is it going to output? It's going to output at f, right? It's going to output this guy. Okay, so that's what it does. And then what we're doing in the previous slide, this thing or this one up here, we're calling this one f sub A. Okay, but now we can call it f sub A because we have a function that given A give us f sub A, right? When you call it something like that, depending on an element, is essentially you have a function that given A gives you the function f sub A. Yeah, so it's a bit abstract in the sense that it's a function which outputs functions, but functions are objects, and a function can output everything it wants. So what is this? This is what this capital F sub A is doing. It gives you from a member of a collection outputs an onto function into the member, and that allows you to put together all these functions into one big function. Okay, are we done? We're almost done. We have a function from omega times omega to A. So essentially we proved that the union of A is dominated by omega times omega, right? We have an onto function going, I guess, that way. But we know omega times omega is equinumerous to omega, so that's equinumerous to omega. So we get that the union of A is countable. Very good. Okay, so let me just quickly mention a couple examples of countable sets. More than anything, just to show you guys how these theorems apply. First, if you have a countable set A, the collection of finite strings of A is countable. Remember, this guy up here is defined to be, this is equal A0 union A1 union A2 union A3. The set of one tuple, the set of two tuples, the set of three tuples, the set of all size tuples from members of A together. Yeah? I guess with the notation that we developed at the recently in the class, you can see these as functions from 1 to A, functions from 2 to A, functions from 3 to A, functions from 4 to A. Yeah? 1 tuples, 2 tuples, 3 tuples. A to the less than omega is a set of all the tuples of all possible sizes. Each of those is countable, right? If A is countable, the set of pairs from A is countable, essentially what we saw before. And then once the set of pairs is countable, the set of triples contain one pair and a single element. So that's also countable. So you have to show a set of quadruples is countable, and then by induction you can show each of these guys is countable, and then a union of countable sets is countable. So the set of all strings of a countable set is countable. Okay, so in particular you will get that, let's say the set of all words you can write, or the set of all strings you can write in a computer is countable, because you have countably many letters, infinitely many letters. Even if you have an countable infinite set of letters you could use, all the things you can write, like all the texts you can write, so long as the text is finite, it's gonna be the set of all those texts is countable. Okay, so you can go too far. Let's say the set of all programs that can never be written in a computer is countable. Another example, the set of algebraic real numbers. You guys remember what an algebraic set is? An algebraic number is? An algebraic number is, let's recall this, a number R in the reals is algebraic if it is the root of a polynomial with integer coefficients, with coefficients in the integers, or in the rationals is equivalent. Okay, so if you can write a polynomial, and so this one is the root, then you get the algebraic numbers, right? So examples are, I don't know, square root of 2 is the root of x squared minus 2. Or you can write square root of 5 over 2 plus 1. You'll find a way to make it. I say there's some polynomial that is going to make it. So that's going to be the root of that polynomial. Fifth root of 3, you have the polynomial x to the 5 minus 3. That's the root of that. So all of these are algebraic numbers. They are not rational, but they are. You can still define them in a nice way as roots of polynomials. And why is that? Well, I guess we have to make two observations. The set of polynomials with integer coefficients is countable, right? Why is that? Well, because the set of polynomials of degree n is equinumerous to z to the n plus 1, right? Because, well, you have the coefficient of x to the n, the coefficients of x to the n minus 1, the coefficient of x to the n minus 2, all the way the coefficient of x, and the free coefficient, the independent term, right? So you have n minus 1 terms, and each one has an integer coefficient. So essentially a polynomial of degree n over the integers is given by an n plus 1 tuple of integers. So there are countably many of those, and you union above all the possible degrees, you get countably many polynomials. And now, so that's one observation, and the other observation is that each polynomial has finitely many roots, right? Actually, a polynomial of degree n can have at most n different roots. You could have less, but at most n. So you have countably many polynomials, each of them with countably many roots, finitely countable many roots. The union of all of those is countable. So there are only countably many algebraic real numbers. Algebraic real numbers, they are a very nice bunch of numbers. They form a field. I don't know if you prove that in algebra. So they form a field, so you can add, multiply, and divide algebraic numbers, and you stay within the algebraic numbers. A field is an extension of the rationals. And it's a field that behaves very much like the reals in many, many senses. In many algebraically behaves very much like the reals. It's countable, so it's still going to be full of holes. It's like the rationals are full of holes. It's still going to be full of holes. It's not going to be complete inside the real. So in that sense, for calculus, it's not that good. But for algebra, it's very close to what the reals are. All right, see you guys in the next video.